Our last presentation today is developments in ATSC 3 and ATSC 1. And we have as presenters Mr. Perry Priestley and Mr. Morton Simonson, who you've met before. Perry, I should indicate, has a long history in television broadcast engineering, and I'm so happy he can join us today and share some of his perspectives on digital television as it exists today. Perry?
Chuck, good afternoon again. Thank you. Thanks for the introduction. I must say I've been really impressed with some of the presenters so far. It's been a truly excellent webinar. It's actually difficult to follow such good presenters, I have to say. So, but I am pleased to be here, pleased that we can do this, and I'd like to get going now, if that's okay. So what I'm going to cover mainly is a product that we were going to show at NAB. I'm actually going to demonstrate live, just like we were going to do at NAB, our digital exciter. And I'm hoping there'll be plenty of time at the end of the presentation for Q&A. You can see here the webinar schedule. So the Elenos Group. It's made up of 4 companies with their own distinct strengths. Elenos for its design in compact and price competitive FM low power transmitters. Telco for its broad range of low, medium and high power transmitters. And Broadcast Electronics for products like, well, studio products like the Audio Vault and high power FM. We also have Pro Television for the state-of-the-art modulation technology, which we heard from Morton earlier, which is both in digital TV, digital radio, as well as analog TV, and now, of course, the combination of analog radio and digital radio, HD radio. Here you see a complete range of TV products from 1 watt to 12 kilowatts, and obviously combining the 12 kilowatt cabinet, you can get up to powers of 50 kilowatts. These come in UHF and VHF, air-cooled and liquid-cooled, and all come with features like hot pluggable modules, ATSC3 technology, and of course all available from Quincy, Illinois. The transmitter that we were going to show at NAB was a transmitter translator, a new product that's aimed towards the ATSC3 market. So what's the difference between a transmitter and translator? Well, translators typically receive their inputs over the air, whereas transmitters have their feeds via direct lines like satellite or microwave, typically requiring an ASI or a 7310 or IP inputs. One of the key commercial differences, though, between a translator and a transmitter is that the translator feeds a much smaller market, and hence the actual product becomes a lot more price conscious. It also has to be quite a lot more reliable, theoretically, than a full service station, as a lot of translators can't actually be accessed for almost up to 50% of the year. And it has to have, well, really has to have consistency between products and between power levels, whether it's UHF or VHF, high power or low power, because usually one engineer might actually look after dozens and dozens of transmitters. So here are 4 key items that I would look for in a translator. With ATSC 3.0 on the horizon, a translator needs to be considerate, a translator operator needs to be considerate that it's not that his normal ATSC1 input may actually disappear. It may not be tomorrow, but it won't be too long, and so it's something definitely to consider. Of course, things like redundancy, remote monitoring, and a key issue, of course, is reliability. These are 4 characteristics that should be on the list when looking for a new product. Taking reliability as an example, moving parts of a transmitter are the first parts typically to fail. And as we've moved in technology from older style transmitters with valves in, we've moved to solid state. They're typically, and in air-cooled formats, usually just have one moving part, and that is the fan. So the first thing to look for is to make sure that any product has at least 2 fans. And if one of those fans fails, that you can still run at, well, at least, a significant amount of power. Also need to have the fact that it's really easy to change a fan. The last thing you want to do after driving 3 or 4 hours is have the struggle of trying to remove a chassis from a cabinet or a rack, and then have to take the lid off and then fight wire harnesses and finally get to the fan to replace the fan. It should be easy to replace. It should take just a few minutes with no special tools. So we talked earlier, Morten talked earlier very much about this new supercomputer and the fact that it now covers every single standard known to mankind. But why would a TV station or a radio station think, well, why is that important to me? I only have one standard, maybe two at the most. Well, a company like BE looks after more than just the United States, or it looks after TV and radio stations around the entire world. So it's important that we support all transmitters of all standards. And the good news now is that one product addresses every single standard there is, including now HD radio. And if you can imagine that, we have one product that can support 60,000 radio stations worldwide, 60,000 TV stations worldwide with absolutely no problem, just one product. Let's take a quick look at the low power transmitter or translator that we were going to show at the NAB, and look at some of the things that we were going to promote, things that we were going to recommend to look out for when buying a new product. First thing I want to mention is headroom. Go for headroom. A lot of manufacturers rate their products typically at the highest power level that the transistor or higher power amplifier can actually perform, leaving no headroom at all. My recommendation is at least 50% headroom. Make sure it has the appropriate AC input AC protection, and make sure it has a self-contained modulator, making installation much easier, and it allows a real consistency between products. Having some future-proof product features like an ATSC3 receiver, and also having an ATSC3 modulation capability is also a really good investment. Although ATSC3 may not be right here today, it may not be needed immediately, it will save a lot of time, a lot of money, and a lot of anguish later if it's actually organized now. So the key to any transmitter, and we've discussed this a lot, especially with Morten talking earlier, is the exciter. The exciter is important because it really does determine the overall performance of a transmitter. It also determines the efficiency of that transmitter or the amplifying system. It often controls the transmitter. It often allows access of the monitoring, and it really does determine the future capabilities or lack of capabilities of a transmitter if not organized properly. OptiPower is an Elenos Group proprietary solution developed to provide an increase in quality, i.e. MER, and efficiency of new or even existing transmitters. With better performance comes typically better coverage, which reflects, in most cases, as more revenue. Look for an exciter that provides every possible option to get optimum performance. MEC, CFR, that's memory error correction, crest factor reduction, and the latest algorithms to improve efficiency and improve MER and IMD. The ATSC3 standard is IP. No more CVBS, no more ASI, no more 7310M. It's all about IP. So why skimp on IP inputs? You really should have at least 2 for IP content input and at least 1 for management, ideally with a second backup. And if your modulator only has 1 MAC address, then it does not matter how many ports you have. If that MAC ID fails, your IP connection fails, you're off the air, and you have no control of the transmitter. Lastly, insist on gigabit capacity. If your modulator only has 100 megabits capacity, then you may limit the entire system network. One of the top priority requirements for ATSC 3.0 is the capability to deliver both reliable low bit rate mobile TV and data services, while at the same time deliver high bit rate, high quality, like 4K or UHD. Layered division multiplexing, or LDM, is a physical layer, non-orthogonal multiplexing technology to efficiently deliver multiple services with different robustnesses and throughputs in one TV channel. The two-layer LDM structure actually is an accepted part of the ATSC standard. This is not to say that if you don't have LDM, you still can't do 2 or more signals. It just means that LDM enables a much higher payload capacity, offering further enhancements like more channels or even better quality. Another must-have, a scheduler. A scheduler, sometimes referred to as a framer or a gateway, defines all the modulation parameters for the exciter and modulator. The scheduler allows the operator to define such parameters as one or more subframes and PLPs, the modulation parameters to be used at frame and PLP level, and the mapping between input and feeds and the PLP. With a standalone scheduler, multiple exciters therefore can depend on the same STL feed and hence can be operated in an SFN network. An internal scheduler, as the one we provide inside our exciter, can only be dedicated to one transmission system, so it is limited to the multi-frequency network. Although not as comprehensive as a standalone unit, an internally configured scheduler is ideal for a single station wishing to test out ATSC, maybe to check the coverage, maybe to see if ATSC theory really works in his environment, maybe just to check if it's commercially appropriate, and without really an enormous investment. MEC, I think Morten went into this in quite some detail earlier on, so I won't talk too much, but typical nonlinear distortion that we normally talk about in a single carrier system is relatively static. Once corrected, and apart from variations of heat and aging, is quite stable. However, there is also involved with high current devices like power transistors a thermal variation, which the device remembers for longer than the actual signal it's being fed. A memory effect, if you like, which causes a different kind of distortion, a dynamic distortion, one that changes with the level of the input. ATSC 3.0 has a higher peak to average ratio than ATSC. It's about 2 dBs, in fact. So the dynamic thermal variations are larger, and hence the memory errors are also greater. Having a good memory error correction system will improve SNR by up to 2 to 3 dBs and is thoroughly recommended in an ATSC3 transmitter system. Same goes for crest factor, or CFR. The better the algorithm, the less crushing of the peaks of the signal, and the less compromise one has to make with SNR versus the out-of-band intermodulation products. The key point here is that if CFR is to have a great effect, you have to have a really good starting SNR or MER. CFR also has the advantage of reducing damaging spikes, such that the long-term effect is you have less failures in your RF amplifiers or even in your transmission line and antennas. Doherty modulation is now a well-established technology. It's installed in hundreds, if not thousands, of transmitters worldwide. It was originally developed for AM and was implemented by transistor manufacturers about 8 years ago, and has since then gone through 4 or 5 iterations of improvement to where we are today. Doherty modulation not only improves the efficiency, but because of the lower consumption, we have a lot less heat removal requirements and the lower temperatures of all, which increase the life of the system components. So because the transmitter is running more efficient, it's running cooler, and most likely will last longer. The question then, because there is a compromise when you do apply Doherty modulation, you typically lose maximum power, you reduce the maximum power, or you decrease the bandwidth, or a combination of both, is when is it better to implement DOA demodulation. If we look at the graph on the right-hand side here, you can see that low powers like 100 watts, 200 watts, you save a few $100, $300 to $600. Now this graph is based on, let's say, 10 cents per kilowatt hour, running 24 hours a day, 365 days a year. But when you get up to powers like 600, 1200 watts, it really does seem that saving $2,000 to $4,000 a year in electricity and air conditioning, it's a well worth investment. So are the RF specifications the same between ATSC and ATSC 3.0? Well, pretty much so, yes. Here is the channel spectrum of an ATSC1 signal. Here is the actual noise, and this is where you would measure in band the signal to noise ratio, or the modulation error ratio. On top of a standard ATSC3 signal, you have a pilot carrier. We have a bandwidth of 5.38 megahertz. And so we measure from the top of the pilot carrier to the lower sideband or the upper sideband at plus or minus 3 megahertz, and see that we get a measurement with respect to the peak pilot carrier of 47 dBs. We have, with ATSC3, which is slightly wider, 5.83 megahertz, we have a similar bandwidth, very similar, but no pilot. The signal to noise, or the MER, is still measured exactly the same, based in the in-band, but the outer band have now referenced the actual center of the carrier. So the specification hasn't changed, the quality hasn't changed, but the actual number has. Instead of 47 dBs, we'll now be looking for 36 dBs. Again, Morten talked a little about automatic and adaptive and linear and nonlinear pre-correction. This is a layman's view of how linear and nonlinear works. We start off with let's say, a 6 megahertz amplitude frequency response being fed into a high efficiency, which means nonlinear amplifier. And out of it, we get a product that's no longer 6 megahertz, but typically three times the bandwidth, 18 megahertz wide, with a lot of intermodulation products. So how do we get rid of those? Well, Morten showed us mathematically. This is graphically what we do, is we need to expand the signal, and we need to feed intermodulation products in antiphase, that's opposite in amplitude and gain, to that signal, and feed it through the nonlinear amplifier. And now, of course, we have the ideal output. Now, still, the output is expanded, so it has a higher peak to average ratio. It's also still 18 megahertz wide, but at the end of the day, it does. We do obtain the actual signal that we do desire. So this was shown on the HD radio. It's the same between radio and television now, that we feed the modulator exciter with what's called pre-distortion signals or feedback samples. We take a sample from the output of the nonlinear amplifier. We take a sample from the output of the bandpass filter. This is the linear or phase error sample. And we feed those back into the exciter, which then generates the equal and opposite gain and phase signals. Those are added to the input signal, and ultimately we have a perfect output. So we now move on to translators and a brief discussion relating to the future proofing of your translator. The question probably on everyone who owns a translator, who operates a translator, is what I'm going to do when all the stations around me are transmitting or an ATSC3 signal and I can't receive that signal. The initial solution would be, of course, to purchase an ATSC3 receiver and a decoder. And then from that, decide if you want to transmit ATSC or ATSC 3.0. If you decide on transmitting ATSC 3.0, then you'll have to purchase an HVAC encoder, an HVAC encoder, as well as an external scheduler. If you decide to transmit ATSC, just that, you will have to buy a lesser expensive, but still nevertheless an MPEG-2 encoder with a PSIP generator. At the very least, either of these options are quite an expensive option, and potentially, most likely, more expensive than even the translator itself. This actual need may put a lot of translator companies and businesses out of business. A solution, of course, to this problem is to employ a receiver decoder that can not only pick up ATSC, but ATSC 3.0, and then deliver either the appropriate ATSC 3 signal or an ATSC signal back into the exciter. If the exciter has the appropriate scheduler function already included, then this board will help any station, any translator station, move to the ATSC 3 environment very easily. Even if you wish to keep transmitting ATSC, which is most likely the case, this will make life very easily. You can swap between ATSC 3 and ATSC transmission remotely, literally the flick of a switch. So let's take a closer look at the exciter, and we're doing this because literally we were going to have a live demonstration of this at NAB. I have with me a live transmitter right now with an exciter, and I'm connected into this, and I'm going to now try to connect to that exciter live. I think I can do that this way. Just wanted to confirm that everybody is seeing that. Chuck, can I get a yes on that?
Sorry, Perry, got called away. What did you have to say?
Can you see the actual live?
Absolutely, live and in color.
In color too. Oh my gosh.
Yeah.
It's almost as good as radio, huh? So here we are. We actually have a live picture of the exciter that's on the air right now, and as you can see, I've got a single transport stream input. I don't have any ASI inputs, and this graphical user interface is made up of 4 panels. The top panel is the entire schematic for the system. Here you would have the ATSC1 receiver. It's actually not in the function I have. And here you would have an RF power amplifier and bandpass filter. One of the cool things about this exciter is that you can really drill into any part of the system, whether it's the receiver, output amplifier, or any of the in-band inside components, just by dragging and dropping the components. So let's, for example, take a look at the input. And we can see here that the input is good. We're running at around, well, a little high there, 20 megabits per second. We know the IP address. We can actually really look down at all the parts, the TS packets per frame, the lost IP, forward error correction, and any current latency. So you've got a really detailed view of the actual input. The same can be done for ASI. I don't actually have a feeder here, but same for either ASI signal. We can then go, and because this is the input side, we can then look at, let's say, the switching, and we can select any one of those inputs, and we can determine how they're switched, how quickly they're switched, and on what condition they should be switched to ensure, let's say, they didn't have the right transport stream ID, or we didn't have the right delay on the PAT, then it could be switched over from the primary to the secondary. We can determine any one of 1, 2, 3, 4, 5 inputs on this switching system. The next part following the input section is the mode section, and of course this is based on right now a multiple frequency network, but we could set up a single frequency network and set up all the necessary delays that are required for an SFN.
Perry,
yes.
In case you wanted, I have one with ATSC3, so if you thought it could be funny, let me know, and just to show the similarity.
Yeah, let me just finish a couple of these, and then we'll flash over to the ATSC3. I think that's a great idea. So
didn't intend to interrupt you, just thought.
Yeah, no, it's It's a team event here. So we've got the mode function here, and then of course we have the pre-correction that we discussed earlier, the linear, the clipping, and the non-linear. And here we can set up, we can actually measure the amplitude frequency response, the group delay, we can measure modulation error ratio, we can measure lower shoulder and upper shoulders, and we can even, if we grab hold of the adaptive, look at the actual frequency response, see that in a large graphic space. You can see now the signal to noise ratio, the lower sideband shoulder, the upper sideband shoulder. And if we want to go to the RF output, we can set the frequency, we can set the power. So it really does allow very easy to drill into any single component, not just in the exciter, but the entire transmitter. And I'm just going to show one more demonstration, and then we'll change, maybe zip over. Chuck, are you there? So Chuck, you'll need.
It takes me a second to unmute. Yes, I'll move it over to.
No problem. Yeah, Chuck, you'll have to give Morton
I understand.
presentation, but I'll just click here and show that it's really easy to simply select a different. Let's go to ATSC 3, and we can show immediately and press reboot. And 30 seconds later, you've changed from ATSC 1 to ATSC 3, and of course change back again.
Hard to imagine, isn't it?
Yep, it really is very easy, very simple to do. Let's have a quick look at the ATSC3 system.
Okay, Morton, I'm changing, and you are now the presenter, and you can share your screen.
Yes.
Whoops.
I hope you can see it. Hello, everyone.
Yes, indeed, we can.
And how an elegant way, Perry, that you say, this is how we change to ATSC3, and here you see it is. For the ATSC3, and I will not do long. I just thought it would be nice to support your talk, Perry. For the ATSC3, you see the similarity is very similar. Now, of course, the inputs are Ethernet. The switching the PLPs and signal pass is from the left to the right. When things are green, they are good. When they are red, they are bad. Again, we see the spectrum, and this is actually pre-correction I'm running on an Untitled transmitter that I do not have in the room with me. It's a little too noisy. You can see the real measurement of the thing is here, but it's the same thing we measure internally on the exciter. Perry explained very well, and I think I will not use too much time because
could you? I would really like if you could show the grab hold of the HPA and bring that down.
Well, you're thinking about the scheduling here.
Yes, the scheduling too. That's excellent.
Yeah. So in here, this one we are running in scheduler mode, and as you see, we have put on some PLPs, and actually we make a graphical representation of how all the channel capacity is distributed. And this is all dynamical things, PLPs you can configure in the ATSC3 standard. It's very comprehensive. It will be exciting to see whom has the fantasy to actually use all of it. But I believe this is one of the better overviews because you get this idea that how much capacity is allocated to where in a more graphical way. You see here we have allocated for PLPs. But I think maybe, Perry, I misunderstood you. Did you ask me for something
also
specific?
The high power amplifier, the HPA?
Yes. So this is actually for a not very high power amplifier, so not in so many features, but it's a little more overview kind of thing. And this is, of course, also intended that in case there is an existing amplifier, you can integrate, if you use our exciter to upgrade that amplifier, you can integrate functionality in a relatively simple way. So we measure the power and temperature and currents and reflected power as well.
Yeah, it's excellent, and that gives you the ability just to have one graphical user interface for not just the exciter, but the entire transmitter system. So just one place to go, and you can find everything, and you can drill into any part of the transmitter really quickly and find out a lot of detail.
Yeah, that's true, Perry. Actually, I prepared this as a demonstration for adaptive free correction, but now I have been running it, and you see the output power MER, as we measured, is above 40 dB, and we have almost 44 dB of shoulder on each side. And so now I think I will actually do the reverse. If I press neutral curve here, we go back to when the pre-corrector have had no activity at all. And then we can see where we came from performance-wise.
Yep.
So I know it's a little reversal of time, but each iteration takes a little time. So I didn't want you to stay here waiting. We can maybe sit and watch one iteration. So I will try to press neutral, and that will show us what was the performance at exactly the same power level without the pre-correction. So here we have a steady state. Indeed, as you said, Perry, things are pretty stationary. Steady state end condition, and now I will press the neutral button. And then it needs a little, like 20 seconds to perform a new measurement. And in the meantime, we will see it quite immediately here. You see, we are going from here. You see it over here now?
Gosh. Yes, it's
This was the improvement of the pre-correction.
Wow.
And you must imagine that the level of noise in the band is here. So we go from something like 17, 18 dB of MER all the way to 40. Imagine you had to do that with the actual dimensioning of the amplifier. That would cost many-fold the price of such a pre-corrector.
Right, absolutely.
See, look, here we are. We start at 18. Yes. And this is, of course, the spectrum.
It's a bad place to start at 18.
It's a bad place to start, yeah.
But it's a good place to end up with the 40, yes.
Excellent. And that's the first iteration. Look, it's almost like 10 dB in one step. There we go.
And this is obviously going to be a very similar sort of correction process to the HD radio X-Gen modulator.
It's completely similar. I could just as well have shown it on that. Works exactly the same way. Yeah.
Excellent. Very good.
So Perry, I really, unless you have something or you want me to go.
No, I think we're about wrapped up. Yeah. Chuck, I think
you want me to hand it back to you, Perry?
Sure, we can do a last page.
We can see your last slides.
Yep, and share my screen.
There you go.
I will mute myself then. Thanks for the visit.
Thanks so much, Morten. How cool is it to be able to switch from Baltimore to Copenhagen in a heartbeat? Boggles the mind.
Indeed, and communicate via transmitter, exciter, web GUIs.
Okay.
All right, so I think we're open for some questions, and while we wait for those to come in, I think we're running a little bit over time, so I won't take much time here. Just to review everything what I was saying, look for an exciter that has all the latest bells and whistles like layer division multiplex, crest factor reduction, memory error correction, minimum of 4 IEP inputs, an amplifier with Doherty modulation. Make sure you have the ATSC modulator capabilities for both 3.0 and 1.0, and also the same for an internal receiver. So I think that wraps up the presentation, and really now open for questions.